What we're going to do when we're analyzing any problems using these variables that I've just introduced, the positions and the velocities, is to look at an object in two snapshots. So it did something initially, and then we let it evolve on its own using the laws of physics, and then we take another snapshot and we think about what it's doing finally. For the initial snapshot, what I do is I define its position, its velocity, and its acceleration in that initial time. What we do to denote that I'm talking about the initial time is put a little 0, as you can see with these variables, below the letter. So we see an x sub 0 and a v sub 0. These are just telling you that this is our initial snapshot, our first look at the object. The way we speak about this, because I don't want to keep saying x sub 0 or v sub 0, is to say x naught or v naught. And this is just a way of speaking so that we can quickly talk about these variables. So you'll hear me say very often through the next few lectures x naught or v naught. And so this is the initial position, velocity, and acceleration of our object. We can look at a different snapshot of our object a little bit of time later. If this was where it was initially, and I let time evolve, where it starts at 1 meter, and maybe to take example values, 1/4, 0.25 of a meter per second of motion, and say we give it an acceleration, as we just saw, of 0.5 meters per second squared, and then let it time evolve. Say we let it evolve for 3 seconds. Then we look at where the apple is after we've let it evolve in time for 3 seconds. And then we look at the variables again there. So the apple at this time has a new position, a new velocity, and a new acceleration. And you can see what these are by looking at the apple, at least the position, because you can see where it is relative to our coordinates. It's at position 4 meters. If that's the case, then we can find the velocity and the acceleration using equations that we'll come to later. But the important thing is that you look at these two boxes, the initial box and the final box, and know that for any problem, you can always take 2 snapshots, and you can choose where those snapshots are going to be. So for example, I could have chosen 2 different times. Supposing I needed, for a given problem, to look at my apple not initially and at 3 seconds, but initially and only at 2 seconds later. That is also something I can do, and we can look at the final or the new positions, velocity, and acceleration of our apple after only 2 seconds have evolved. Looking at our graph on the bottom, you can see that the new position of our apple is at 2.5 meters, and it has a new velocity, which we'll be able to solve using the equations we'll get to soon. Turns out to be 1.25 meters per second, and in this case has the same acceleration because we've just kept the acceleration consistent through this entire time interval. For the next example, what I'd like to do is return to this basic picture where we have initial and final separated by 3 seconds and introduce some ways of talking about the change from initial to final and what that looks like. So just taking this example, like I said, of 3 seconds, there are 3 quantities we can talk about when we're discussing the change from an initial position or initial setup to a final setup. First is how is the position changing? How did the position change from where it is now to where it was before? We call this the displacement. And in fact, anytime we're talking about a difference or a distance between 2 time frames or 2 snapshots of an object, you can always find the distance or the difference between initial and final by taking what we call a delta x, which is just a notation meaning that the change in x. So when you see delta, it's just telling you change in x, by taking the final position minus the initial position. That might sound like a strange definition for change, which you might not be familiar with, but you can see it works very well. Because if I asked you how far did this apple go when starting at 1 meter and going all the way to 4 meters, you would say it moved 3 meters. But the way you find this mathematically, in case you were met with a much more complicated situation than an apple moving by 3 meters, is you can take where it is finally and subtract where it was initially. And you can see, as we hope, we get 4 minus 1, or 3 meters of displacement as this apple moved off to the side. But we don't need to just talk about the displacement in space. We could also ask about what about the velocity of our object? If this object is changing its velocity and it has an initial velocity and then has a final velocity, what is the average velocity over this time interval? The reason we say the word average here is simply because instead of asking you the velocity which is changing moment to moment to moment, I just want the average velocity over the entire time interval. And to get this average velocity over this entire 3 seconds, what I would do is take the displacement, the total change in position, and divide by the total change in time, which in our case is 3 seconds. Doing this, we see that from our displacement of 3 meters, we have 3 meters divided by 3 seconds. So the total average velocity of our object is 3 meters every 3 seconds, so 1 meter per second of motion. Finally, as you might expect, we can ask about the average acceleration of our object. In this object, as we saw, we kept the acceleration the same the entire time. We held it at 0.5 meters per second squared. But we can still ask ourselves about the equation for the average acceleration, and it will be the exact same. It will follow the same principles as the first two, which is that you take your change in velocity and divide that by your change in time and see how the velocity is changing per time. The total change in velocity we just found was 1 meter per second, but the final velocity minus the initial velocity would be a simple way to do this as well if those were the variables that you knew. The final velocity we saw from our problem was 1.5 meters per second, while the initial velocity was only 0.25 meters per second, and the same time change of 3 seconds. And so we can do this very simply. Subtract 1.75 minus 0.25 and see that we have, as we hoped and expected, an average velocity which is equal to our average acceleration, which is equal to the acceleration we held our object at through the entire interval, which is 0.5 meter per second squared.